Hello everyone. In this step, I'm going to be explaining how an AI is created from the very text that goes in to generating a response at the very end. There are three distinct steps, which is the tokenizer step, which takes the text, turns it into tokens, because computers, they can't work with words, they work with numbers. So you make all the words into numbers the computer can understand. You train the model on these tokens that the numbers that the computer can understand. At this stage, after you finish the training stage, you're already ready to generate responses, but they're not curated to users. So depending on how the training went, it might repeat a lot of sentences that it saw or not give it in a format that lends itself well to user interactions, which this step fixes. The biggest step is obviously the training stage. The next most important one is the generating phase, but all of these steps, the reason I've made them distinct is that all of them can actually be skipped in favor of the other one. So you can grab an already made model and then just work on making it generate better responses. You can grab an already prepared tokens and then just feed them to the training. All of these are skippable, but we will be diving into how to get us starting from step one. So we'll be talking about the vocabulary stage, what you get when you put a text in and it turns it into a token. Now, one of the most important parts here, and the parts where you can save a lot of information, is how you process the information. So you have the word tokenizer. So you take whatever word it is and you make it a token. So the black lines here, you just take the full word and make it into a token. Alternatively, you could break the words into parts and feed that into it, or you can do byte pair encoding, which is taking every character as its own byte and feed that into making it a token. Now, obviously, the smaller you go, the better your AI is going to be at the very end, but the more it's going to cost you to train it. But obviously, an AI that learns characters is going to be much more flexible, is going to know much more words, and overall is going to be much superior, but it's going to cost a lot more. So you take those characters, you turn them into tokens. These tokens are basically numbers that the computer can understand, and then you run the byte-pair encoding training, which gives you the vocab, which is all the numbers that it understands, and the merger. Now, I will have to explain what a merger is a little bit more. So, for example, a merger takes, for example, T, and like it takes all these words that and capitalization matters as well, and sees that okay, T and H happen to be appearing next to each other a lot. So T and H are a token now, and then it might see T, H, and E appear next to each other all the time. So it makes that a token, and then might see T, H, E, and then a space bar, and then that's a new token. All these steps matter, and basically it's just in this phase is predicting what tokens come next to each other, and makes it into a merger text so the computer can understand this. Okay, moving on. This is here where you take this part, you take all the text files and all these vocabs and mergers and everything you have, and you make them into a really big bin that the computer just digs into for all its information and learns off of that. So in this step, you make the bin and then you set the model parameters. I talked about this before, or maybe after, I'm not quite sure how I'm going to edit this video, but this is where you set the vocab, the layers, everything. You set your model parameters here, and then you start the training loop. And be warned that once you start the training loop, you can't change the model parameters without running the training loop all the way from the start. And the training loop is billions of steps long, so it's going to take a lot of time depending on the system you're using. So you really want to make sure your parameters are exactly what you envision for the model to use and the model needs to do the task you need it to perform. After billions of steps are over, after all this training is done, or even before that, you will still have your PTH file if you make good checkpoints. Basically, all the checkpoints and the final checkpoint are all PTH files that the generating phase can call on to generate the AI responses. So at this stage, you're actually done. You actually have an AI that can respond to prompts. It can do everything a normal AI can do. You're done at the model training stage. But what we move on to next is the curating phase, where the model, maybe it read a lot of books, so it's generating text like a lot of books, like what did Hamlet do? Hamlet went and shot someone. So you obviously, users referencing another Hamlet or something like that, you want it to be curated to more of a chat based perspective rather than the AI just regurgitating whatever it learned off the training data. So here, the most specific thing that changes AI to AI, how they respond, is adding special tokens. The most obvious special token that everyone's probably familiar with is the stop token. So when the AI knows, hey, I should probably stop generating text at this point, which, for example, you might see this in a lot of AIs where they just keep talking and talking and talking, maybe repeating themselves or giving useless information. That means the creators have a bug with their stop tokens. But the AI stops responding because it hits a token limit rather than the stop token. So this step is actually very important to making your AI's responses unique. What responses come where they basically putting like empty holes for the AI to fill. So you put a square hole, you put a triangle hole, and the AI is like, okay, let me form this response in the form of a square and put it here. This is a triangle, it goes here, and it learns how to respond in the specific format that you want it to. The next step is learning through human feedback. Now, this is very, very important, and it's one of the most essential steps in fine tuning the AI to making it sound more realistic and believable. There's a lot of ways to do this. The most frequent one is the reward token one. So the AI gives you a response, you give it a like token. Hey, this was a good response. Here's a reward. You did great. And then the AI is going to repeat that behavior as many times as it can, where it gives the most amount of rewards. And when you give it a downvote, it's like, yeah, don't respond like this again. Now, this depends on how heavy it is. The frequently the character, like a human's response, the individual's response doesn't weigh that much. Obviously, a scientist's response when creating the AI, they're going to put their own reward system. So, for example, a response from a scientist that created it, he's going to put it like, my reward is worth 1,000. You can take everyone else's rewards as one or two. And that's how their reward system works. That helps the AI learn, which, yeah, this is why they open it to the public so the AI learns through talking with, liking the response ultimately makes the AI a lot smarter, but it's, something most people don't want to do. There are other ways to do it. Like I said, the AI could have features to where it could learn on its own, but that's more deep learning stuff that I might get into later. And yeah, at the very end, at this stage, like you're pretty much done. Here, you add all the accessory steps, like how you want the AI to generate its text. So greedy, for example, based on the stuff you give it, is going to generate the same text every single time that it thinks is the best possible response to you. Sampling is it takes the sample of K and V, and it takes basically a sample of the tokens, averages them out, and gives you the best average of the samples that it chose. You can have it not even respond if the AI is only communicating with another computer piece or another AI. It will write a JSON file so the other AI or system can easily read it. You can use a catch to make the responses cheaper by putting some stuff in memory and a whole bunch of other stuff like setting the temperature, the variability, all that stuff. But yeah, now you know exactly every single part that goes into an AI, from the text that it learns from at step one to generating very curated, very smart responses at the end of this last step right here. And yeah, with this being over, in the next one, I'll be talking about the AI code that I wrote. If I can pull it up right here. This will basically be just an example of what we went over. So if you want to see an example of how it all goes, so this is a token, just makes the tokens. It gives you the vocab and generate the merges. These are tests. This is the model. So remember, if you change your model, the checkpoint won't work. So in your brain collection of all the previous checkpoints, you need to have a pair of model and the checkpoint, so you can replace the checkpoint and the model of your device system, and you will have basically a new brain for your model for your AI to respond with. Or you can not change your model and only change the data, and then your checkpoint's going to change, but your model is going to keep the same answer just with new data. These are the different generators. I did not go too deeply into these right now because I don't have humans to give me a lot of responses, so I only have a gradient sampling, which lets you pick a batch of samples before. Hello everyone, welcome to this video. In this video, I will be showing you the example of the AI model that I have coded. Now, the reason you might be seeing these metrics and think they're kind of small is because I've trained them all locally on this computer, and they're meant to serve as a starting point. This code was mainly written to learn. I have adapted it to work with something else by setting all the logs to a JSON, which another app will interact with. That's just a project I have for in the future. That one's goal is to make a desktop assistant that basically does all your menial tasks for you. But let's focus on this video, shall we? So yeah, we will be going in order. So tokenizer is where your data goes in, model is where your data is trained, and generator is where your output is generated. So we will be going in that order. Normally you'd see more options. For example, I put my train model here, but that's irrelevant. I will be giving you all the information as we go. So let's start with the tokenizer. Now we're using BPE, which is byte pair encoding. That means splitting the text into their byte level and learning off that. So you get that's the best result. That's the least amount of effort you can put in for the best results. And this is the vocab. This is just a best recommended vocab that I found out there. It gives you basically all the good, relevant English dialect. For example, the, hello, all that stuff gets saved. So this is a number that I have heard to be the best. This right here, this is where your text gets split into code for the computer to read, because the computer can't work with normal English text. It works with bytes and hex and all that stuff. So this is where you encode it. I guess right here. This is where the merging happens. So you break them down into byte levels. You see T and H appear next to each other a lot. You make that into one token. You merge them together, and they replace all the instances where T and H go together with this new token. And you keep repeating this until the merging is complete. And basically, after this, you get a file, which is your merger text, which shows the AI, when it's learning, what the most frequent pairs are. Sorry if there's another spoke cut. So from this point on, we will save it as a hex, if I can find it. I will be going a little bit faster because I notice okay, I'm going fast. So then we save it as integers, which we encode them as integers. And then this guy reads the JSON, which is the hex files. And then the encoder encodes it from byte to integer. And then the decoder goes from the byte to the integer, from the integers to the bytes. So you have to encode everything, and then naturally you have to I realized a mistake. It's train, not to be. So encoding integers byte to integer, and then decoding byte to integer. No, I think I said correct. Sorry. And then the load interprets the hex file. After all this is done, the JSON gets saved. So we have both a merger and our JSON ready. And that's basically what we feed into the AI for it to learn. One thing right here is kind of important. You want to replace all the errors you might get with like question marks or something, so that your training can go smoothly even if the way you coded it runs into an error or something unexpected. You want to account for that stuff, because at this point, catching errors is very important. You will notice later on that for reasons, because every computation second or millisecond matters because you're dealing with such high data. Catching errors at that point, you have to be very, very efficient with it. But at this stage, because it doesn't take too long, make sure you debug your code very. Moving on to the model. So here, basically, the token is going to be split into, we're going to start working with these tokens. So we're going to split them into basically very large vectors that relate everything to each other. So one token is now going to represent, like in my example, 256 possible roads and groupings that it can have. The more it is, obviously, the smarter it is, but the harder it is for it to analyze and understand it. That's why block size matters so much when we're doing this stuff. I have explained all this stuff. This is the number of heads. Basically, after you split into layers, you split it into heads. If you want more information on this stuff, I would recommend you watch my previous video, but just to save some time, I will be keeping this information very brief. Actually, I will be going over them very quickly. So layers, after you get your information, you split how many layers that you have, which is how many times information gets processed. Number of heads means the different perspectives or different ways you analyze the information. Layers is very heavy, number of heads isn't very heavy, but gains is diminishing. So it's recommended to have a fair number of heads. Moving on from this, we're going to be, after this, we calculate all the attentions, which is very quickly, I would like to explain that the ideal method to go about doing this is to get all the attentions and then feed the attention to something called softmax, and softmax develops a percentage, like after feeding forward, feeding backwards, how good is this item to call, creates the weights for your model, which the model uses to generate responses. However, that is old technology at this point. Advances in this field are very, very rapid. The stuff I explained might seem a little off from what you might read, but there's just newer steps that I found online when reading the GPT guide. So just keep that in mind. That's the reason you might see some stuff that you might not see in the old textbooks. So something you're going to see a lot in this version is the RMSNorm. What norm is, right here, this place is the place to focus on. What norm is basically, because normalization basically exists to control the scale of activations between the sublayers. This is basically just to have a range. For your training, you don't want any spikes. You want a smooth, basically just a smooth line as close as you can be to it to help the learning go smoothly. So RMSNorm, the aim is to make sure that it stays within a expected range, so we don't get a very high spike or a very low spike. It's for consistency. You will see this called a lot in the other places, like the transformer. Find the transformer right here. This is the transformer LM. This right here is basically where you turn the tokens that you've received, the tokens that you got from the tokenizer, you turn them into embeddings, which is something that the model can actually interact with and learn from it directly. You will see later on that the D model is 256. What that means is that every token input that comes in here is made into a vector of 256. So basically, it's like a grid with 256 slots where information can be stored to. And each one token gets split into these 256 tokens. This is what the model can use to relate words to each other. This is what it does when it's doing its learning part. I have gone into learning in more detail in my previous videos, so take a look at that if you want to know exactly what happens in this process. But this is basically where one token is taken, split into a lot of information, and that information is used to help the model determine the relationship between the words, that the tokens that are coming in, which are later turned into words. The next topic we will be looking at is the QKV, if I can find it right here, QKV. So this is what the question is, This is what the question is. K is what do I contain? What information do I have? And V is what information can I give if I am selected. This will be used to compute the attention later on, and the attention is used to set the weights directly using tools like softmax, but the tool I use is slightly different, which you can see right here. So this right here is the attention, and this right here is the output. This is one of the points of contention. Some people would say the naive implementation is better, but for my specific systems and low-end computation, This one saves a lot of memory because you leave out the middleman, which is compute processing every single query and adding the heads to it independently. And this just processes it all and applies the mask retroactively, like at the same time. So it skips out an extra step, which is eats a lot of memory, but some would say that is more important for the memory, for the AI to learn properly. But like I said, it's an exchange at every single step, and this is what fed to what I was planning to do better. There are, of course, new tools being developed to speed up this process, as created as libraries at every step. One of those examples is the GLU, which speeds up the process, but basically all of these steps do have a library to make them faster, which is something to take into consideration whether you want to write them from scratch or to use a library. If you write it from scratch, of course, you have more flexibility and you can set it to be more efficient and such, but it's basically just a trade-off. So that's a decision the coder would have to make to use a library or to code them themselves. Moving on, we have the transformer block right here. The transformer block, there are a bunch of other steps, but this is nearing the final steps. The transformer block this is basically the final step. You apply all the norms here. Basically, the product is ready to ship, everything is applied, and you can see right here how simple and how much room there is for improvement. You apply the norms, and then it's a simple addition. Arguably, you can make this more complex. You can add a lot of stuff here. At this stage, a simple addition is sufficient for the calculations to go forward. And that's where we reach the LM, the transformer. So this is basically it. So if you want I'll summarize this section. Basically, at the very end of the day, you have the forward pass. You put in the token IDs, you get 256 embeddings, which are the grids, the vectors I mentioned. You add positional embeddings from the positional embedding. You pass through 4 transformer blocks, all the stuff I mentioned. This includes all the stuff like SwiGLU and RMSNorm, all that stuff. And then you apply the final RMSNorm another time, and then you project the vocabulary logits via head. The output shape should have the batch size, the sequence length, and the vocab size, which those are all parameters that we have already set, or the parameters that got inferred from the items we set previously. Moving on, I will touch on the data sets and how the data is being fed. There were other legacy forms. The data loader, this one takes in a text file. This was the block size, but the current one is the Parquet one. Those are older versions, but they still function. So the current one is the data loader of Parquet. So it takes a Parquet form and streams it. Block and segmenting is a lot better, but if you're working with lower end items, it's better to stream it, because for blocks you would have to load everything into RAM. The learning is a lot better, of course, but you would need a lot of RAM and a lot of GPU to process that. Streaming, you actively stream it in. One number goes in, one number goes out. It's a stream. So something that's pretty important for Parquet is that Parquet are advertised as a lot of big data centers like a Hugging Face puts everything in Parquet format because it's essentially is advertised as ready to be learned by an AI. So everything is grouped up, every information is basically spoon fed into the AI. You would have to account for all these different groupings. So, but if you end up getting it, you can have a very, very large data set. If you look right here, these data, for example, each of them are 400 megabytes, and there's a lot of them, because you need a lot of information to feed these. So just this one on its own is probably 400 megabytes. That's equivalent to 400 books. So you need a lot of information to feed it. You want the easy spoon-fed items to give it. I will not dive very deep into this because there's a lot of different formats to use. This player is very flexible. I would personally recommend Parquet because that's what the data scientists are currently using. And it's the best approach to go until a better format comes along where everything is literally the same. Right now, things are just grouped up, so it's easier to learn. So I will not dive too deep into that. We will go directly into the training. This is arguably the hardest, the most computationally expensive part. It's not even that many lines, so I have a lot of outs, a lot of debugging statements. Obviously, you want to get this as short as possible because this is the most computationally significant part, even if it's just printing out the steps, printing out the plateau, checking metrics. all this stuff should be taken out in an actual official training, because you want to save milliseconds on milliseconds, because that stuff adds up. I just have these because I'm working on a personal scale. Having the logs and stuff to look at helps me understand where I could improve my current design. But if you're doing it, don't even have try, don't have any outputs, just run the training, no output, trust your own code. Or your mentors or peers will double check for you to make sure that everything is working fine, so you don't have to output or write anything to a JSON or anything like that. So the training. These are the hyperparameters, block size and the batch size. These two basically determine how much information your AI sees once during training. Obviously, the higher this number, the bigger the context it has to learn, and the better it is. These are the heads, the layers, the D model. I've spoken about this. These were very prevalent in the model. It calculates everything else. Right here, these are the steps. I have these on my computer, so I can like run the training and I can leave the house, leave my computer on. So it trains it the whole time, and then I come back and maybe like I leave the house for a while. So I did have a plateau, a total number of steps for each session. I didn't want it to get too crazy, but probably in a normal one, you would manually stop it or just have the checkpoints, because you're guaranteed to for it to stop at the end. You might not even need checkpoints necessarily. So this stuff, it is necessary if you're doing it on your own. For a business, probably not necessary. It's just going to slow it down. We will get to this later, but this right here, the PTH, this is basically your AI's brain. You plug this into your AI and it can start generating responses. This is a collection of all the weights, everything like that, and it's the most important part for having your AI to respond. This is the item that part one, the token, and the model, the training was all leading. Yeah, we will get to that later. I would like to do a quick explanation of gradients. I've noticed it. So what gradients are, you calculate how much your model is learning or not learning, and you save that as a gradient. And based on what the gradient is, you make an effort to reduce or increase the learning depending on the loss. Obviously, with a low context in streaming, gradients are very harder to work with as opposed to the segmented or the block learning, where you preload a bunch of blocks and you move forward with that. But it is still sort of relevant in streaming. It could be. So it's important to have them regardless to keep your model from spiking. It's like the norm. You basically want to keep stuff from spiking or going too high or too low. If you are curious as to the exact place, it should be in the thread. This is basically where the gradients get used. There's a lot of logical information, of course, but this is basically where gradients get used to plateau the loss of the item. So I'll show you LR lambda, which uses a cosine plateau to learn rate right here. So what this does is, you might be thinking, oh, the more you learn, the better, but it's much more important to have consistency than to just learn blindly. So this would cause a spike normally, but with the lambda using the cosine, you will have it be a more free flowing. So you gradually build up and then you're allowed to learn through it's balanced by the other steps as well. But basically, this just because the gradients at the very start are randomized when you open a file. This is just to make sure that nothing spikes or goes crazy and you end up learning to an unnecessary degree in one area while the rest is lower. This is just to control that. You like learning a lot or learning more in any step is not necessarily a good thing. What we're aiming for is consistency. So obviously, you're learning about all this stuff. The next natural step to take into consideration is the checkpointing, if I find that. So basically, when you start from a new area, a new checkpoint, all your gradients, everything will be reset unless you make preparations and step to prevent that from happening. That's it. So you check your OS path, you find it, and you save it there. Like just this. Oh wait, what's going on? Yeah, okay. So learn it from here. You save all the steps. For me, it's 500 steps, but I made it dynamic, obviously. Everything has to be dynamic. This is the checkpoint, and you resume from the checkpoint, and everything is saved from the loss history, the start step, everything like that, so the starting can be seamless. I would assume for major companies, they don't even have to write this part. It just runs infinitely until it's at a satisfactory state, but I believe this is smart inclusion for my program, at least. Moving on, an extra thing I would like to mention is a step for efficiency. You're fighting a lot for efficiency here. So if it's actual active streaming, you would have to wait and stall for the next buffer to fill up before you put it. So you can get stuff and put them in a queue, as you can see right here. And once you put them in a queue, it actively calls it again so that the queue is always full and it can just actively fetch from that queue. So you can fetch from the queue instead of waiting for the buffer to be filled up again at every single step. I believe that's all the general information needed. The rest of the stuff will be in generator. Now, speaking quite frankly, my generators are not very impressive as of right now. I only have a greedy and a sampling. But this is the step where basically you put in the stop token, you put in the temperature, you put in all the stuff you would visualize show to the user. Obviously, in this step, feedback from an actual human is very important, and this is why many companies release their AI for free so they can get this feedback, because feedback is so important to an AI for it to know how to respond. So, but for me right now, I have a greedy and a sampling implemented. Greedy basically responds at the same time and picks the best option every time. Sampling takes a top K and top P and basically grabs a sample of them and generates a response, which is more random than greedy. It gives you a new response every time, but obviously without user feedback, both of them are just going to repeat what they read in a book or something along those lines. Okay. This video has gone on way too long already. I will cut it short here because, as you can see, it's debugging. There's not much to show at this step because I don't have users to give me feedback. So yeah, that was the example of the AI that I have coded. Everything for it works. Obviously, the main constraint was the lack of high RAM or GPU for me to train it on personally. This was all done on a AMD laptop, my personal, and I did start getting feedback. The responses are coherent after 2 weeks of training, so I would consider it efficient for my needs and purposes. The future of this will be, this is the where the user, I don't have an interface for it yet, so you just edit this to give a prompt into AI. So yes, the future of this project, I am hoping to integrate it into a JSON. Of course, I might be giving the responses myself so it can operate with the assistant that I plan on coding in the future. But this was basically just a snapshot into the project that I've written so far for anyone that might be interested in AI or just as an evaluation of my current coding ability and knowledge of these topics. Thank you very much for your interest, and yeah, I hope you have a good one.